Hi, my name is Win Lei. Today we'll be talking about the topic of MapReduce, why it is important to use MapReduce, and the attack vector was mentioned in the research paper that we'll be discussing today. The topic will be observing and preventing leakage in MapReduce. First of all, I want to give credit to all the researchers at Microsoft and Professor Divya Sharma at Carnegie Mellon University, who have worked together and discovered the attacks and how it can be used against MapReduce framework. The topic was presented at the 22nd AMC conference on computer and communication security. You can find the original paper in the link below. A little bit about the content of the presentation today. First, we'll talk about the background on MapReduce. What does it mean for big data, cloud services, and then we'll go into the potential problem with MapReduce framework. We'll define the adversarial models, the attack vector that will be used from these adversaries. Lastly, we'll talk about the prevention mechanism. There will be two algorithms, shuffle in the middle and shuffle in balance, will be discussed. And then we'll talk about the results and the outcomes on applying these algorithms to the data sets and the MapReduce framework. The background about MapReduce. Today, we have tons of cloud services, for example, Uber, Twitter, Facebook. For the government, we have healthcare, transportations, chemical industries. So all of these services have cloud infrastructure that generate an enormous amount of data. This data can be about the user information, how user use a certain service. An example would be Facebook. They are generating data on how people are using their system, what posts they are interested in. The goal is to generate ads revenue. They're targeting ads for you. E-commerce sites like Amazon, they monitor user information to suggest more goods, more items for you to buy. Now, on a day-to-day basis, lots and lots of data are being generated that way. The companies use this data to optimize itself, to improve sales and other means. They need to process in a fast and efficient manner. That's where MapReduce comes in. So MapReduce is basically a distributed computing model, and it's a pattern within the Hadoop framework that is being used to access big data stored in the Hadoop file system. And then the structure of MapReduce framework is it comprised of mappers and reducer functions. Each of these units can be viewed as a single machines or virtual machines in a cloud setting, right? And they are communicating with each other to produce the result. So how does MapReduce work? And we will be focusing on the open source implementations of Apache Hadoop. So MapReduce comprises of mappers and reducer functions. What are they? So mappers is a function that takes input records, and produces a list of key value pairs based on certain criteria defined within the mapper functions. So it will deduce the key with the value aggregated with it. So these sets of key value pairs will be sent to a reducer, which has an aggregation function that will collect all these keys and produce a final result, an aggregated result on that key. And to the environment that these functions runs in we can consider it as a secure hardware, meaning input data and storage data are encrypted. So essentially, no plain text being sent over the wire at any time. Mappers and reducer functions in our settings and in the research paper are run in a secure regions. So what is a secure region? Basically, mappers and reducer are viewed as trusted containers. You can think of it as a Docker container that's running on a virtual machines um, on top of the physical machines. So these isolated containers are trusted container and secure. Um, so if you look at the image below, we can view the job as, there are documents, very, very large documents being sent to a mapper functions in a secure environment. And the end result of the mapper is another set of key value pairs, smaller sets of key value pairs being aggregated in the mapper layer. And these key value pairs will be sent to reducer functions to process. At the end result, you would get a key with a certain value. Could be a number, could be a string, whatever that we define within the reducer function as a single result. And all of these communications are being encrypted, data are encrypted and secure. An example of MapReduce would be the traditional counting words in a given document. Imagine that you're giving billions of documents, text documents, and the task that we want to do is to count the appearance, the frequency of each word in these documents. We can have a settings, an example in here would have 3 mappers, each process a large number of documents. The result of these mapper would be words, how many times a certain words appear in the input documents, right? So for example, cats appear 10,000 times in these documents. The word a, the, and appears X number of times. The job of the reducer functions is to aggregate these key value pairs. They aggregated the word cats in several mappers and then produce a final result. So the reduce function in this case is a simple sum. The aggregated function used is a sum function on all the dedicated keys. The final output here would be the word cats appear 100,000 times in these input documents. Now we'll dive a little bit deeper into the problem with MapReduce that were mentioned in the research paper. As we mentioned earlier, MapReduce framework were executed in a secure hardware and in secure regions. Data are encrypted. However, traffic can still be monitored between the functions because MapReduce framework is a cloud settings where their mappers and reducers are dedicated instances that does not keep states. So informations will be sent from mappers to reducer, and then at the end produce a result. So the communication layer can be observed and exploited given the right settings. We'll be talking about 2 types of adversaries and then the potential problem that MapReduce could expose. So there are 2 types of adversaries that can compromise the system and infers information from these jobs. The first one is a system level adversary where he has access to the network traffic and can analyze the volume that being sent over the wire in terms of bytes, packages, number of records. And this adversaries can also control resources and scheduling of the mapper, not necessarily the data itself, but how mapper works. They can feed in record one at a time or in batch to control how the job's being processed. And from observing the data between, they can infer information about that particular data. The second type of adversary is the application level adversary. This adversary may have background knowledge about the job itself, the inputs and the outputs. The information about the job may be available or can be inferred from the shape of the traffic data. Statistical information about the input and the output, etc. So you can find things online, for example, birthplace, people in the US, public information like that from hospital you can potentially look up online. And then the important concept here is called intermediate traffic from MapReduce framework. It is defined as the traffic between the mappers and the reducer because the mapper has function that process key value pairs from the input data and produce certain format. If you observe this traffic, you can infer if you know what's being fed into the mapper, what type of data is being fed in there, and then the formats being produced by the mapper, you can infer information about it. So how do you exploit the intermediate traffic, right? So the model that we define here, that we're gonna define a matrix A of size M and R, where M is the number of mappers and R is the number of reducers. The matrix entry MR is the number of intermediate key value pairs sent from a particular mapper to a reducer. Since an adversary observes an input and output of every mapper and reducer, you can construct this matrix easily. So if you look at the example down here, you can see that every mapper reads 3 encrypted records. And in the entry, in the matrix, each entry indicates how many intermediate key value pairs produced by the M mapper have zip code that's returned by the R reducer, for example. So one attack, this thing leads to something called a job composition attacks. And how does an attacker use this matrix, right? So an adversary observes matrix A from each job and can infer information about the data as long as the same input data is used again, right? So you can label each input batch with the result of the inference. Now in the research paper, the researchers are using census data on zip code, gender, and date of birth of people to identify, and then the attacker can identify people uniquely given that they monitor the traffic. They understand what's the input and they monitor the traffic between mappers and reducer. So there are 2 types of exploit on intermediate traffic. An adversary can use individual record, can feed in individual record to the mapper and then observe the output, or they can do it in the batch settings. So the first attacks are based on observing mappers as they consume one record at a time and immediately produce data out of it. The intermediate traffic matrices before had 1 row for each record. And at least for basic application jobs, each row has exactly 1 non-zero entry. So given the adversary is will be able to answer specific queries on any combinations of these attributes, such as given an index of a record in the data sets, return the values of these attributes. He can test if the dataset contains a record that matches particular values for some of these attributes, and also given the values of some of these attributes, infer the possible values of others in the datasets. The second type is called batch records. This applies against mappers that securely process a large batches of records at a time. And we assume that each mapper reads all records in a batch assigned to him, applies the M mapper on each of the record, the M functions on each record, and returns the list of key arrow pairs as the same process. Now, observing the aggregated job yields an intermediate traffic matrix A with fewer rows. And then we assume that there is a reducer for every key. So again, by observing matrix A in the batch settings, the adversary can perform the certain tasks, like given an aggregated count of the values of the attributes in the data sets, he can infer precisely the counts of the attribute values over smaller batches of data. And then given prior information about a specific record, like public information, for example, it can infer other attributes related to the data set itself. Now that we know a little bit about how the attackers can utilize information about the data to attack, we'll talk about the security definitions and how to prevent, and then we have to define the security model, and then we can work back into how to securely implement the solution to prevent these attacks. So in the research paper, we formalize the definitions and then reduce it down to 3 important concepts. We can view the attacks on a framework as, and then the combat between the attacker, like white hat researcher, or we trying to prevent the attack and an adversary as a game. We can model that as a game. And basically, at the start of the game, an adversary would pick 2 data sets, D0 and D1, and would fix the number of M and R for the mappers and reducer. He then is given access to D, where D is either D0 or D1, and he can observe multiple MapReduce job of his choice. He observes the full network traffic and guess whether it's D0 or D1 in the settings. Now, if he gets it correctly, he wins the game. And then the output of this is the probability of guessing it correctly. The second concept is correlation hiding. That's required no efficient adversary has more than a negligible advantage in winning the MapReduce game. And then for every MapReduce job the adversary picked during the game, the following properties must hold. Mappers produce the same amount of output. Reduce function takes the same amount of input. The output size of the reduce function R is constant. And then the third properties or definitions is called strong hiding. This requires that no efficient adversary has more than negligible advantage in winning the MapReduce game as long as the size of D0 and the size of these ones are the same. And for every MapReduce adversary picked during the game, the following properties must hold. The volume of intermediate data is the same. The number of records for the most popular key is the same. The output size of the reduce function R is constant. Now, given that the security model is defined, definitions, we talked about the definition, and we're going to dive deep into how to use shuffle in the middle to mitigate the attack. So at a high level, shuffle in the middle is basically a technique to prevent intermediate traffic analysis on the MapReduce framework by introducing a shuffling step before we feed the data from mapper into reducer. So if you can look at the images down here, we can see that there's a shuffle steps in between mappers and reducer instead of just feeding the record directly into the reducer. And then on this side, basically we have the algorithm on the mapper side and then the algorithm on the reducer side as well. So given the encrypted data sets D as an input, the shuffle yields some permutation pi of D as an output. Since D can be large, we want an efficient implementation of the shuffle in a secure map framework. So each mapper takes an input, a permutation pi, an example, and a batch record of B. The output bins of max record for each reducer, that is an R bins in total. The mapper assigns each record D in the batch to one of the R bins according to the permutation tag as being pre-assigned. And then the reducer takes a list of bins, removes, and also there is a step to append dummy informations to essentially create a padding behavior so that mappers and reducer we can have consistent amount of data per our security definitions. So the data being transmitted are the same. On the reducer side, when it's processed, it will remove these dummy values before processing by the predefined pi tag. The second approach is called the shuffle and balance implementations. Basically, it's a very similar process, but it involves two phases. One is offline, one is online processing phase. You can refer to it in the images below. So this view basically introduced the offline shuffling on the input data. So it's trying to prevent the attacker from knowing which data sets are being fed into the mapper functions. It doesn't have control on what's being fed in. And also there will be the online phase where it being broken down into a sampling state and then the actual main processing job. The idea is to essentially create a statistical information from the input data. For example, how many what is the number of keys represented in the sample set? Its frequency, what is the most popular key in the sampling sample size of the data? Using these informations, you can infer information about the larger data sets. And that's information will be fed into the mappers and reducer when the main job runs. We talked about the concept of mapping and bin packing. The goal is to produce a secret assignment between the mappers and the reducer to properly assign the bins, properly assign the reducer from a given mappers. Similarly, you also want to do padding on traffics to fix the size per our security definition, so that reducer it's eliminate the fact that adversary can observe informations in the traffic layer. So now I'll go a little bit into the analysis of the results. The current settings that we performing is a Hadoop cluster of 8 nodes, each with 2.9 gigahertz on an i5 chips, 8 gigs of RAM, 250 GB SSD. Solutions being implemented on both Java and C++. The result will perform on 2 data sets, the census data sample and the New York taxi rides. And from the result of these 2 algorithms states that the shuffle imbalance yields a much better performance than shuffle in the middle. The reason it has more steps involved in terms of shuffling the offline processing, find out the statistics of the data before running the actual job. So basically, shuffle and balance has more information about the data set itself rather than shuffle in the middle, where it's just simply doing the random sampling in between. And interestingly, because MapReduce framework is being executed in the parallel manner, adding more padding and shuffling the offline processing does not really affect the performance of the Hadoop jobs. Now, however, when this shuffle in the middle applicable, it can be used if the offline processing job is not an option in a certain scenario. So there is still value in using shuffle in the middle for offline processing. So in the table on the right is basically the runtime of applying these algorithms on the 2 data sets, and you can clearly see that shuffle and balance wins here as the runtime is a lot better. And that will be it for our presentation today. And I hope you get a general idea of what the attack vector is, what's the general concept of MapReduce. Thank you.